Hi everyone! In this section we'll look at objects that are subject to Newton's first law. Newton's first law is also called the law of inertia, and it says two things. An object at rest will remain at rest, or an object in constant motion, which means that it's moving at a constant speed in one direction, will remain in constant motion unless acted on by a non-zero net force. So mathematically what this means is that if the net force acting on an object is equal to zero, then its acceleration is equal to zero. It does not accelerate, which means that it can either be at rest or be moving at a constant velocity. And the opposite or the inverse applies as well. If an object is not accelerating, its acceleration is equal to zero, then its net force is equal to zero. So we know that an object is moving subject to Newton's first law if it's A, either not moving, so it's at rest, or B, it's moving at a constant velocity. So look out for those terms because they tell us that the net force, which is the vector sum of all of the forces acting on the object, must be equal to zero. Again, the net force is a vector. So if the net force acting on an object is equal to zero, this means that its components also equal zero. So this means that the net force in the x direction, or the x component of the net force, which is the sum of all the x components of the forces acting on the object, has to equal zero. And the sum of all the y components, the net force in the y direction, has to equal zero as well. So there are some simple steps for solving problems with Newton's first law. First, we're always going to start by drawing a free body diagram. So draw your diagram, show all of the forces acting on the object, at least all of the forces that we're looking at in the question, and make sure they all start at the object and go outwards from the object, so in the direction that it would be pulled by that force. Then you can use a coordinate system. So I'm going to always use the standard coordinate system. Well, at least in this section, we'll use the standard coordinate system, the XY system, where to the right and up is positive and down and left is negative. If you're using anything else, make sure that you clearly state that so that I can follow your work. And then secondly, we'll write out f net x and f net y and set them equal to zero. Once we've done that, we can solve for any unknowns in the problem. Remember that these are forces and their components need to have a direction, so make sure to add signs to your components. We'll look at one 1D problem to practice, and then we'll go on to some 2D Newton's first law problems now. Example 3, a 5 kilogram book is resting on a table. It is pushed downwards with an applied force of 10 newtons. What is the normal force acting on the book? All right, so let's always start with a free body diagram. I'll draw it here. We have the normal force, it's resting on a surface, and then the force of gravity downwards, and we're pushing down on the book. So we need that applied force that's also downwards, and I'm using again the standard coordinate system. Up is down, up is down, up is positive, and down is negative. And then what we're going to do is use our net force in the y direction. I'm not going to write the x direction here. That is also equal to zero, but there's no forces acting horizontally on the book. So one thing we can do first is find the weight. Fg equals mg, and we have a 5 kilogram book times 9.8 newtons per kilogram. So 49 newtons is the weight for the book. Now, when we write out the forces in the y direction, I'm going to write them with their correct orientation. So I want to add them all up with the right sign. I have Fn, that's up, minus Fg, which is down, minus Fa, which is down as well. And we can do this because they're all in the y direction. Okay, then I'm going to solve for the normal force, that's the unknown here. So Fn equals Fg plus Fa. So that's 49 newtons plus the applied force, which is 10 newtons. So the normal force in this case is 59 newtons. Note that this is a good example of when we do not have the normal force equal to the weight. The normal force is greater than the weight to support the applied force that's pushing down on the book in order to keep the book at rest. Example 4. A 55 Newton suitcase is pulled with a force of 12 newtons directed at an angle of 20 degrees above the horizontal. The suitcase slides at a constant velocity over rough ground. A, what is the magnitude of the friction force acting on the suitcase? And B, what is the magnitude of the normal force acting on the suitcase? So let's begin with a free body diagram. Here's the suitcase. We always have gravity. It's on a ground. You don't have to draw the surface, but you can if you like. Then we have the normal force, which acts perpendicular to the surface. It's being pulled, so I'll draw an applied force here at an angle of 20 degrees. So I'm choosing that it's moving in the positive direction. You could choose the other direction, but make sure that friction opposes that. So since it's moving to the right in the positive direction, friction has to go in the negative direction and act parallel to the surface. So friction looks like that directed to the left. Okay, so in the first part, we want to find the friction force. That's our unknown. That's horizontal, so I'm going to start with the net force in the x direction equal to 0. This is a 2D problem, so we'll need to use F net x and F net y to solve. Okay, so the sum of the x forces have to equal 0. We have two forces with x components, friction, and this component of Fa, which is Fax. So I have Fax, which is positive, minus friction equals 0. This means that the horizontal component of the applied force has to balance the friction force so that it can move at a constant velocity. Constant velocity was the key word to tell us that it is Newton's first law and that the net force does equal 0. Okay, so now I'm going to put in the components. This is a little triangle here, and notice that our x component is adjacent to the 20 degrees, so it's cosine. So I'm going to have Fa cos 20 for the x component here, minus friction equals 0. And I'd like you to get into practice of writing your components in your net force equation line, because sometimes the force will be our unknown and we'll need to do that to solve. Okay, now we can solve for friction just by moving it around. So friction equals Fa cos 20. So that's 12 newtons cos 20, which is 11.3 newtons. All right, now in part B, we want to find the normal force. The normal force is vertical, so now let's look at this net force in the y direction is equal to 0. So in the y direction, I have the normal force, I have gravity, and this vertical component, Fay, of the applied force. It's opposite to this 20-degree angle now, so I'm going to use sine for that y component. Okay, so back down here, I have Fn plus Fay minus Fg, which is down, equals 0. So now let's put in the components, Fn plus Fa sine 20 minus Fg equals 0. And then I'm solving for this normal force, so we get Fn equals Fg minus Fa sine 20. We were given the weight in the question, so pay attention to the units. We were told it's a 55 Newton suitcase. So that is Fg. We have 55 newtons minus 12 newtons sine 20. And that gives me 50.9 newtons for the normal force acting on the suitcase. Example 5, a traffic light is suspended between buildings by two wires as shown. The right wire is at an angle of 25 degrees to the horizontal, while the left wire is at an angle of 15 degrees to the horizontal. If the tension in the right-hand cable is 250 newtons, what is the mass of the light? Okay, so free body diagram, we have the tension in two cables, so FT1 and FT2. You can just label the tensions with different subscripts to indicate that they're different values. And then FG, which is down, and using the standard XY coordinate system here. This traffic light is at rest, so we want to check, and we know that since it is at rest, the net force in the x direction and the net force in the y direction will be equal to 0. In the previous questions, we've been able to solve one of these at a time, but sometimes we need to solve one in order to find an unknown that we're looking for in the other. So another note that I haven't drawn a normal force here. If the object is not in contact with a surface, then there's no normal force, right? That's a force that arises from surfaces pressing together. All right, so let's start. Let's say we go to find the weight. We're looking for the mass, so eventually we're going to do m equals Fg over g. So this is our first unknown. And it's in the y direction, so let's start with the y direction. When I do this, I have two components, vertical components of the forces here and here, the two y components of the tensions, Ft1y and Ft2y. So we have Ft1y plus Ft2y minus Fg equals 0, since Fg is down. Then putting in the components, they're both opposite to the angles, so they're both sine. So Ft1 sine 25 plus Ft2 sine 15 minus Fg equals 0. Now when I try to solve for Fg, notice we have two unknowns. We don't know what Ft1 is or Ft2. So when we go to solve for Fg, notice that we have two unknowns. Fg is unknown and also Ft2 is unknown. We know that the tension in the right cable here is going to be 250 newtons, but we don't have the tension in the left cable. So right now with two unknowns, we can't solve yet, so let's go to the x direction. Net force in the x direction is equal to 0, so I have Ft1x. Note that the tension forces are each pulling horizontally. Ft1 is in the x direction here, and Ft2 is in the opposite direction in the x direction. They're also both adjacent to the angle, so both will be cosine. Okay, back here. So Ft1x minus Ft2x, which is to the left, equals 0. So that's Ft1 cos 25 minus Ft2 cos 15 equals 0. So solving, I get Ft2 equals Ft1 cos 25 over cos 15. So 250 newtons cos 25 over cos 15, which gives me 234.6 newtons. So now that we have that unknown tension, we can go back and we can solve for Fg in this equation here. So now I'm going to rewrite that and solve for Fg. So we were starting with Ft1 sine 25 plus Ft2 sine 15 minus Fg equals 0. So we get Fg equals Ft1 sine 25 plus Ft2 sine 15. So that is 250 newtons sine 25 plus 234.6 newtons sine 15, which gives a weight of 166 newtons for the traffic light. And now that we have that, in the last step we can find the mass. M is Fg over g. 166 newtons divided by 9.8 newtons per kilogram to get 17 kilograms for the unknown mass of the traffic light, and that's our final answer there. Example 6, 3 dogs are pulling with just the right balance of forces such that a ball remains still. Dog C is pulling with a force of 159 newtons. With what forces are dogs A and B pulling? So we're given the free body diagram in this case. I just want to point out that we're looking down on the ball like this. So this is a 2D plane, and we're only concerned with this plane. The normal force and gravity would be in the third plane, kind of here, coming into and out of the page. but they're balanced and they don't provide any more information to the problem, so I'm not going to draw those on the diagram. Since we have two unknowns in both x and y, we're going to need both f net x and both f net y here. And the ball is at rest, so we know that Newton's first law applies. Okay, let's start with f net x. We'll write out both equations. So we have f net x equals 0. In the x direction, I have fax here, and I'll draw here fbx. Okay, so to the right, fax is positive minus fbx, which is to the left, and that equals 0. So we have fa. This is adjacent to the 30 degrees if you draw in the triangle here. So that's fa cos 30. Then I have minus fb. This is opposite to the 45 degrees, so I'm going to use sine 45 since sine is opposite of a hypotenuse, equals 0. So I get fa cos 30 equals fb sine 45. And notice I can't solve for anything here. If I could find one of the unknown forces, I would, but there's actually two unknowns. So we're going to need another equation, so let's call that equation 1. Now we'll go to the y direction. Again, the sum of all the forces in the y direction equals 0. My red pen for this, so I'm going to have this y component here, fay, which is opposite to the 30, so that will be sine. And then this is the y component here, which is fby. That's adjacent beside the 45 degrees, so cosine. And then this is our third force in the y direction, fc. And they all have to balance in that y direction. Okay. So we have fc minus fay minus fby equal to 0. That's fc minus fa sine 30 minus fb cos 45 equals 0. And again, two unknowns here, fa and fb, are the same unknowns. So at this point, I'll call that equation 2. And we have two equations and two unknowns. So you might remember from math that a good way to solve this is by substitution. All right, so let's rearrange equation 1 for one of the unknowns. I'll solve for fb. So from equation 1 here, I have fb equals fa cos 30 over sine 45. And I'm going to plug this into equation 2. So this is going into equation 2 for fb. And this will eliminate that variable so that we'll have only one unknown. So I'm going to have fc minus fa sine 30, just rewriting equation 2 here. Now minus, instead of fb, I write fa cos 30 over sine 45. And I still have this remaining cos 45. And that equals 0. Okay, so now we know fc, we have only one unknown, which is fa. So let's move fc over, and I'll change the sign on the left side. So fa sine 30 plus fa cos 30 cos 45 over sine 45 equals fc. And I want to factor out fa so that I can isolate for it. All right, so I made some more room, and now I'm going to factor out fa on the left side. So in the brackets, I have everything that's left. Sine 30 plus cos 30 cos 45 over sine 45, which equals fc. And then I'll divide by this entire bracket to get fa by itself. fa equals fc over sine 30 plus cos 30 cos 45 over sine 45. And now we can plug in that number for FC here. So that was 159 newtons. We have 155 over sine 30 plus cos 30 cos 45 over sine 45, which gives me a force for FA of dog A, which is 116 newtons. Okay, and then that's the hard part. Now that that's done, we already arranged, if you remember from equation 1, we had already isolated for FB. We found that FB equaled to FA cos 30 over sine 45. So now that we have one unknown, we can just go back and plug in for the second unknown. So that's going to be 116 newtons cos 30 over sine 45, which is 142 newtons. So these are our two answers. We have the force from dog A is 116 newtons on the ball, and the force from dog B is 142 newtons. And this is probably one of the most challenging Newton's first law problems, so take a second to look through that and then let me know if you have any questions.